All right, so I updated the OpenCL interface that we've been making a little bit. So it's a little bit nice to work with now, but it also supports 2D kernels, and we're gonna try that out today. So let's make a new folder here that we're um, gonna call it Mandelbrot because that's what we're gonna try to implement. And we have the OpenCL start, and we're gonna copy the the interface to here. It's just the way we're gonna do it right now. And we can also just copy the run thing. That'll be nice to have. And we can also copy the new file. I think we had some stuff in there, and we can call it main. Then let's go here and check this out. So maybe we'll make a kind of changed my mind. Let's make a new one, completely new file, and let me disable this one, and we can make the main function here, and let's say done, and return 0. And now if I go over here and say run main, it should just run that. Okay, so what do we want to do? If we open up this thing and we search for Mandelbrot, then you will see here, we want to try to create this image. And I won't really go in too much detail about how it works. The only thing that's kind of interesting for this, I think, is that every pixel can be calculated independently of every other pixel. That means that this is like the easiest kind of parallel problem you can get, because there's no dependency between the different things that you need to calculate. What you need to do then is you kind of have to run this function again and again. So you have to say square a complex number and add something that will give you the new complex number. You square that, you add the same thing, and so on and so forth. You always start from 0, and this number is determined by the pixel you're at. So if you're here, C is one thing. If you're down here, C is another thing. And Z is always starting from 0. Squaring complex numbers is also something that, or like how complex numbers works, is also something I won't really talk so much about. But let's see if they have an example. So there is an algorithm here that you can kind of follow, and we'll basically do this. Yeah, so let's give it a try. I implemented a way to get a kernel from a file. So what we can do is we can say, let's call it something. Let's call it mandelbrot.pl. Okay, and here we can make a kernel that will call Mandelbrot. And it's going to take an integer array that we can call iterations, that will store the number of iterations that this kind of algorithm has been taking. So you can see here we're also kind of like doing something with the iterations. So it's going to take that, and it's going to take I think a width and a height. And then what we can do is we can get the x index, and now we'll run a 2D kernel because we want to make an image. So there'll also be a y index, which you get like this. And then first we should check that we're not like out of bounds, because you can get out of bounds depending on the width of the image versus the width of the kernel. So this is just always pretty good to do. So if you're out of bounds, we do this. Otherwise, we can actually calculate the index, which will be something like this. This iterations array is just flat, and here we'll have the index into this where we want to store the value. Okay, so now we need C, and that has two components, has the real and the imaginary. So we'll say C real is going to be determined by the x. So we will cast that to a float. Then we'll divide by width. And we want it to go for like reasons, mathematical reasons of how this works. Let's see if we have a plot. The interesting regions like from 2.5 to 1.5 to a half. But for this, we'll just make it go between -2 and 2. So the way we can do that is this number will now go between 0 and 1. So we can multiply it by 4. Now it's between 0 and 4, and then we can subtract 2, so it's between -2 and 2. And we'll just do the same with the y, which is the imaginary component. And here we should divide by height. Okay, then we should also declare this thing that we're going to iterate, which starts at 0. Set imaginary, also 0. And then we can have the number of iterations, which starts at 0, and like the max iterations, which we'll leave at 100. And you know what? Because we are kind of like we're trying to make an image, let's make it end at 255. Because later we'll use the number of iterations we've made as kind of the intensity of a pixel. So then we can say while it's less than this, we want to do, where was it? We want to do this operation. Okay, so z squared. How do you get that? Well, I think we need a temporary real, which will keep track of this one. The imaginary one, we can say it's z real times z real, times imaginary times 2 plus c imaginary, and z real is temp real. So actually let's put in the new value of z real here, which should be z real times z real minus z imaginary times z imaginary plus c real. So we calculate basically the new value of the real part and calculate the new value of the imaginary part we're using the old value of the real part, and then we set the real part here. Then we have to remember to increment this. And here we can say, basically we want to say iterations at this index equals this. But a way to make it look nicer is to say, sorry, if we actually reach the end, then we're going to do something else. So if we reach the end, we're actually going to say it's 0, so it is completely black. That means only the border of this structure will get a color, so it's going to look, it's going to, instead of this where it's like white inside and then black, we'll get a white edge and black inside and outside. So it's kind of nice. But this is the parallel algorithm that we're going to run, and there's no communication between the different pixels. It's just each pixel on its own. So let's see how this interface now works. First, we have to initialize the GPU, which is setting some stuff up. Then we have to de-initialize it. Then we have to set up the kernel. But since we're using a file, we can go ahead and do setup kernel file instead, which I have defined a little further down here. So we need the file name, And what was it we called it? We called it Mandelbrot.cl. And the name of the function is also Mandelbrot. So we have to do that. Then we need to add some arguments. So we should decide on a width. Let's say it's 1000 pixels wide and 1000 pixels high. And then let's make this iterations array. So it's going to be width times height times size of image. And then we have to get the buffer here. We have to make an argument, supply an argument to the kernel. And this is something that we want to write to. So we have to say it's an int buffer argument that we want to write to in the kernel. What index is it? So what does that mean? That means which number here is it? And it's the first one, i.e. 0. What's the data? It's this thing. And what else do we need? What's the array size? That's width times height. All right. What's the next thing? We need to add the other arguments. And what are the other arguments? The other arguments are, I think we do add int arg, it's at 1, and the value is just width. And we do the same here, but it's height. And actually there's one more thing we maybe want to do. Let's say there's an aspect ratio, which is like load height over width, and we can just kind of multiply that here, because then we can do things like, let's make like this kind of aspect ratio. Let's try that, and then it will still look correct. Right. So we add the arguments, and then I think we just say we run it. So run kernel 2D. And we have to say that the result is an integer, unfortunately, because I couldn't make it work otherwise. So we say we want to run for width and height. And let me just copy this. So x is width, y is height. The result is this buffer here. And the CPU result is just, we want to put it back into this one. Let's try to run it just to see that it doesn't break. So it ran, but we cannot really see anything. So what I think we're going to do is go to stb, get image write, and we just download it. So we get it into downloads. So now we can say copy downloads stb image write, get that over here. And then we need to include that. So we do it like this. Then unfortunately, this stb image write only works with bytes. So we have to say maybe we can put bytes into the kernel, but I just haven't really gotten around to that. And then we can just like get the iterations, but turn them into bytes. Can remember to free them. And here we can then use this function to make a PNG. So we can call it output PNG. This is the width. This is the height. how many components are there? We haven't done anything with colors, so there's only one component. The data is just the bytes, and the stride in bytes is kind of between different rows. So that's width times size of the chart, just to be completely clear. So we didn't need to copy it again. Let's try to run it, and there is a seg fault. Which is interesting. Where did that happen? How about we do this? Because we were able to run it before, and we get a seg fault here. So is it this one? Am I using that wrong? No, it's not that. Size of int. It's probably something very silly. We have the iterations, we can run it. It's just in here something goes wrong. Or if I do that, there is something in here. Width times height. Width times height. What if I say array size width times height? And I just replace this width times height. Replace that with array size. Okay. Still this is a seg fault. This is bytes. Int, sorry, I accidentally wrote int. Okay, we run it, and that's it. We got an image, I think. Here it is, output. So let's look at that. And it's completely black. So that's not good. That's not right. Afraid something else went wrong. Interesting. So could it be this? I mean, that shouldn't, but bash. Show me the image. No, it's not that. And that's very bizarre. Let's check out the kernel again. What if we just try to do this? Just write something in there to see that it is doing something. So it is doing something. Now it's all gray. So that rubber, and if we do, yeah, this shouldn't be necessary, but just for fun, let's do that. And it's completely white. So that kind of implies that this algorithm is wrong. Okay, and it's wrong because we also have to check if real times real plus imaginary times imaginary is less than 4. Because if you are greater than 4, then you already like exit. You don't nothing. Yeah, we need to break. Okay, so finally it worked. And there you have it. We can run this algorithm. And just for fun, let's try to make a version that only runs on the CPU. So we can copy main and call it CPU.c. Why not? So we have it here. We don't need this. We don't need this. This one we can keep. This one we can just do like this. We don't really need integers anymore. This one we can get rid of. This one we can get rid of. And in the end, we can just free it to be nice. And we can actually also do that right here. Why not? Even though we don't need to. Okay, so bytes, iterations, and we can say output CPU just to check that they're the same. And we can almost copy this thing into, we can even make a function just to really prove that it's the same. What did I do? So copy all of it, please. Yes. And this one we don't need. And okay, so now we can also kind of like maybe get a better understanding of what the CPU is doing. GPU, sorry. So this stuff, the kernel on the GPU is automatically like dispatched to a bunch of different processors with different IDs. But on the CPU we don't have that, so we have to say, we have to manually loop over it. And I think we can do this. So we loop with all that. That means we don't need this because we just declared it up here, right? And we already know that it's within the bounds, so we don't need to check that. And we can indent it. So we have the index. Everything else is basically the same. Everything else is the same. This one we can also make a single byte. So why don't we do that? And I think that should do it. Now we just need to say call that one on the iterations with the width and the height. And we'll see if that works. So the danger is that this will be so slow because it has to do basically 1 million iterations of something that's relatively complex, that it may take forever. So let's try to time it. So it occurred to me that it's going to take literally 1 million times longer to run it on the CPU. So even if it takes 1 millisecond on the GPU, it's still going to be like 20 minutes, and 3 milliseconds is going to be an hour or something. So let's try to make this a little bit smaller and see if we can run that. And even that might be too long. We'll see. Okay, so that also seems to be way too long. Let's try to just do something really, really small like this. And it's running. While that's running, we can just double check. I mean, there shouldn't be any bugs or anything. Should just be exactly the same code. I'm a little bit surprised that it's taking this long. Maybe I want to try something just, 5 by 5. That should be doable. And you know what we can even do? We can say, let's go to step. And we can say running step, whatever this is, and then I think we can do this to make it look nice. So let's see. It doesn't seem to be working. Let's try this new line. Okay, so that worked. It's some reason stops on that one, and that's because it has to do a lot of iterations. I think. So we can even do some kind of stuff here. So let's do a couple spaces, iteration, this thing. We're getting some minuses, which is unfortunate. So for that, and this is also in, so that's probably a bug, to be honest, that we should also, here we don't have it, so that, there wasn't a bug over there. But, I went into the wrong one. Yeah, we shouldn't compare different types. So let's try this. Okay, so that makes a lot more sense. It's a lot faster. So it was due to a bug. But in any case, let's try this. We have unused variable. And that was also quite fast. So let's try 500 by 450. Also quite fast. Let's see that it's actually correct. It looks correct. And it is surprisingly fast. Let's try this one. So I'm actually surprised it's this fast. It's even basically the same speed, which is weird. Maybe there is a problem in my run. So what if I just try this? And it is the same. But if I do 2000, so there it was a bit slower. And this, let's change that, 2000. So yeah, you need kind of a big resolution apparently to really see it. So this one we can run it under a second. This one is probably going to take a long time. 2 seconds. Okay, so it's not a huge speed up. It's actually not a million like I thought. That was also the naive estimate, to be fair. But I am surprised that the GPU is not a lot faster. So maybe there's something in the implementation that's missing. But for now, let's leave it at that, and I will see you in the next one.